This is lecture 12 of condensed matter physics 1, and in the previous lecture we started discussing quantum Hall effect, the first part. Today what I am going to do is explain quantum Hall effect in terms of whatever we did in the previous lecture and discuss the subtleties of it. Just a reminder as to what we have learnt. Number 1, experimental fact. If you plot the Hall resistivity, which is the same as Hall resistance, versus the applied field, it shows plateaus. So, as you decrease field, I will go this way in the field, you get these h over e square 1 over n or 1 over nu plateaus. So, this may be nu equals 2, nu equals 3, nu equals 4 and so on. Classically, you would have expected a result which is linear. And if you look at the conductivity at these, the longitudinal or rho xx, it shows these spikes where the plateaus change, and we want to explain this. What we did in the previous lecture was looked at a sample 2-dimensional sample that had this 2-dimensional electron gas, and let a current go through this I, and when a magnetic field B is applied perpendicular to it, there is this Hall voltage that develops between the two sides. And Hall resistance R equals V Hall over I. Let me call this x y, taking the direction in the current to be x and direction perpendicular to it in the sample as y, and this is also same as Hall resistivity in 2 dimensions. So, this is also same as E y over j x, and this is quantized. Theoretically, what we set up last time is that when I look at this 2-dimensional gas in the sample, and I will tell you what the sample is, whether it is infinite in extent or finite in extent, we found the wave functions of the electron psi, which is a function of x and y, nth level to be those of, this was same as psi n harmonic oscillator x. So, let me write this n and k and e raised to I k y. The corresponding energy does not depend on k, it depends only on n. So, there is no dispersion where omega c is the cyclotron frequency. The velocity, average velocity is 0, because the velocity in y direction is p plus e a divided by m. And we work this out in the Landau gauge. So, let me write this in. The final result should be independent of the gauge. So, we have this 2-dimensional electron gas in which we have psi x y equals n a k subscript, psi harmonic oscillator n x, plus there was this h cross k over E b. Wave function was shifted, and I will show you in a minute what it means. And this is I a k y. And in this, if I just look at it from one side, this is x direction. You have many harmonic oscillators. The centers differ by 2 pi over L y, where L y is the distance in y direction over which periodic boundary conditions for e raised to I k y are applied. So, along x there are many of these levels. We make them like this, and these are all what are known as Landau levels. And because there are so many of them, each with energy E n, so energy is E n equals n plus a half h cross omega c, there is a corresponding degeneracy that will be all the levels together, and the degeneracy is equal to the flux over phi naught, which is E over h phi. I can also write degeneracy per unit area to be B over phi naught, which is E over, this is not h bar phi, this is not h bar, this is h. So, this is the degeneracy of all these Landau levels. You may wonder whether we put 2 electrons in each or 1. The answer is 1, because suppose I take one particular Landau level, which is nth level. This also gets split due to interaction of spin with the magnetic field. So, this is each level with degeneracy equals E over h phi or E over h b. Again, I am making a mistake here, it is b per unit area. So, this is what we had set up. Now, I can give you a very simple explanation for quantum Hall effect, and that is as follows. In this sample, here is E x, here is b, and when I apply these two, I showed you yesterday that electrons tend to drift this way with speed v y equals E over b. So, let us write it E x over b, and therefore, the current in y direction, I am not worrying about the sign, is going to be equal to the number of electrons, charge in each electron v y, and since this is a surface current, so J y is current per unit length, and n is number of electrons per unit area. and this is equal to n e E x over b, and therefore, rho x y, which is E x over j y, is b over n e. This is the classical result. But because of these Landau levels, now things change. I have these Landau levels, and each with degeneracy equals b over phi naught per unit area. Now, suppose I have nu of these Landau levels filled. So, the Fermi energy would lie either in this Landau level or somewhere in between. This is my Fermi energy. All these levels are filled and these are empty. So, these are filled levels. And this tells you that n is going to be equal to degeneracy times nu, and this is per unit area. So, this is degeneracy per unit area, and this gives you b h over E times nu. Substitute this in here, you get rho x y equals b over this is E over h or h over E. One second. Quantum of flux is h over E. So, let us see now b over h b over E E. I think it is the other way. Let me just see what is the quantum of flux. I may have made a mistake. H over E is the quantum of flux. So, this is going to be b over phi naught h over E. So, this is going to be E over h. I made this mistake. So, this is E over h times E nu. So, I am going to cancel this b, and this comes out to be h over E square 1 over nu. So, you see that because these Landau levels, those which are below Fermi level, are filled, they carry certain number of electrons per unit area, and because of their degeneracy, the whole thing set comes out to be such that rho x y comes out to be quantized, and nu here is the number of filled Landau levels. At very high field, at very high B, the degeneracy is going to be enormous, and therefore, you see only 1 or 2 or 3 Landau levels filled, and you see that quantization. So, what we have seen is that picture that emerges, and I am going to keep making it again and again. Here is epsilon f, and suppose these are the Landau levels, filled Landau levels, nu of them, then rho x y comes out to be h over E square 1 over nu. And this is going to be in very high field. So, you start the high field and you see this. The interesting thing is, even as you reduce the field, this persists and then suddenly it changes. Then you reduce the field further, it persists and then changes, and so on. And that is something we have to understand, and let me explain what I mean by saying that we have to understand this. You see, I deliberately made this Fermi level between two Landau levels, but if a Landau level is filled, suppose I just make it like this. The Fermi level is the topmost fill energy state. So, what should happen as long as this Landau level is filled, you get this number h over E square 1 over nu, and as you reduce it, it changes fractionally. So, it should happen like this. What you are observing is that it continues to grow like this. So, when you are reducing the field, reduction of B, what does it do? Reduces degeneracy, number 1, reduces gap between Landau levels. So, what should happen is, if I make these two Landau levels extended, as you reduce the magnetic field, the Landau level would shift, then make a jump and then shift. So, process should be continuous. What you are seeing is a plateau, and then it changes to the next level. What is happening? And this is where something called the disorder in the material or the impurities play a role. Although I have explained the quantization of rho x y, I still have to explain sigma x x going to 0, equivalently rho x x going to 0. And that is easy to understand. As long as Landau levels are not completely filled, electrons can get scattered by low energy scattering to other states. So, that will be carrying current carrying thing. That will happen certainly where Landau levels are not filled, but as long as they remain filled, you get very small current. So, this is how the longitudinal conductivity is going to be. So, that is also explained. So, rho x y equals h over E square 1 over nu, and sigma x x is explained. Now, we have to explain this plateau, that it persists. So, let us see what would happen. So, again I am making this extended Landau level. There is another one, and suppose this one is filled. This is epsilon f. As soon as you reduce, so let us go to the reduced B field. What would happen? Let me show by the width of this level the degeneracy. This degeneracy goes down, this degeneracy goes down, and therefore, the Landau level, the Fermi energy would shift here. So, what you would see is that you get in rho x y, some rho x y h cross over E square 1 over nu, then it changes continuously and goes to the next level, goes to the next level. You do not see this. For this to happen, what should happen is that this nu should remain for some time, and that happens if you have Fermi energy stuck somewhere between the Landau levels. So, as you reduce B, the Fermi energy goes up, And if there are these disordered states out here, which would happen if there is impurity in the system or there is disorder in the system, the extra electrons get stuck here. These localized states carry the extra electrons, and EF is stuck there for a range of B. So, if EF is stuck there for a range of B, this implies that number of filled Landau levels below EF remains unchanged. And if that remains unchanged, what is going to happen is that rho xy is going to remain unchanged. This implies so does rho xy. So, you see this plateau, and then again you shift to the next level as you reduce the field further, next Landau level. Then you see a jump in the conductivity because that Landau level is slowly filling up, and then again the level gets the Fermi level gets stuck in impurity levels again. So, this is how you see these plateaus coming in. So, this is the explanation. So, disorder in the system is important. So, some disorder giving localized states between Landau levels is important to have. So, this is how you see these plateaus. Now, the second topic I want to cover now is looking at this whole thing through edge states. Or what are also known as edge modes. Again, I will make that picture where I have the sample and I have these Landau levels. Let us look at the ground Landau level here at different points. So, here is this potential. All over. Now, you see earlier I had taken the length of the sample in the x direction to be Lx, and that is how we got the degeneracy to be equal to Lx Ly B over H over E. Now, this is kind of assumed that we are talking about infinite sample even in x direction. Inherently, this was assumed that sample is infinite in extent in the x direction, and you can say Lx is the periodicity of identical systems. So, that there is some sort of a continuity, and therefore, all these electrons in the x direction moved a constant potential. So, electrons are not confined in the x direction. But what happens if the size of the sample is finite? what if Lx is finite? Well, Lx is finite because this is periodicity, so this is a wrong question to ask. What if sample has finite length? Let me go over to the next slide and explain this again. So, what I am talking about is, this is my infinite sample, but what if it is finite? Sample has finite length in x direction. So, what that will be represented by is there is some sort of a confining potential out here. This would be the potential in which electrons will be moving, right. So, this implies a confining potential at the edges. So, now electrons are moving in this potential like this. And there are these Landau level states. All the way like this, and they will be filled up to some E Fermi. Now, let us apply a potential difference delta V across. So, what would happen is that this potential would look something like this. The Fermi energy on this side would be higher, Fermi energy on this side would be lower, and this difference is E delta V. The Landau level states are like this. There is this extra Landau level on the right side where the potential energy is higher. I am not worrying about the sign right now, which way is what, but this is what it is. Now, this potential V x can be written as V at whatever that point is, x 0 plus dV dx delta x plus so on. So, if I keep only this term, then this is like having an electric field where dV dx is not equal to 0. So, what you see is that in this potential, here is some electric field, here is some electric field, and that means I have, in addition to the applied magnetic field, this electric field. And what we saw in the last lecture was when I have these crossed E and B, electrons start to drift. So, there will be a drift velocity V drift, which will be the electric field divided by B, which will be 1 over, since V is the potential, E V is the potential energy. So, I will just write it as dVx divided by E. So, these electrons start drifting, and now let us go to the next slide. What I have shown you is that when I apply this field, I have this tilted potential. This is EF on the left hand side, EF on the right hand side, and these states are filled below EF. So, there is one state right here which is in the gap. So, I have an extra electron which is moving in y direction, and that gives Jy. So, this extra Landau level on the right side gives a current which is unbalanced. So, when I apply this voltage difference here, there is a Landau level which gives a current which is unbalanced. So, applying a potential drop across x direction gives me a current in the y direction, and let us calculate the ratio of that current in the field. So, this current Jy, taking this Landau level to be one level, is going to be E over Ly, that is the linear density of the charge and its velocity, which is E over Ly times 1 over Eb dV dx. In general, I got to count current due to each of this and add it up. So, what I am going to do is net current because the potential in between could be anything. So, as long as this potential is below the EF, this could be like this, and here are these Landau levels. So, everywhere there could be a current, and I will just add it up. As long as the potential does not go above the Fermi level, I can do this summation and calculate the current. So, net current Jy is going to be E by Ly 1 over Eb dV dx integrated over x over the sample length. So, I will integrate it over the sample length times the density of these Landau level states. Remember, each Landau level state is between 2 pi b Ly by 2 pi. So, this is equal to this Ly cancels, I get E over 2 pi 1 over Eb, there is something more here which I am missing, times dV by dx would be V left minus V right. Remember, this is the energy, V here denotes the energy, and this distance delta x was h cross k over Eb delta, which will be h cross over Eb, k is delta k is 2 pi over Ly. So, density of Landau level states is going to be E B over H cross Ly over 2 pi. So, if I take this here, I got to multiply by E B over H cross. I took that Ly over 2 pi. So, this is going to be 1 times E B over H cross. So, what do I get? I get in this potential in which I have these Landau level states, and E f on the two sides is different. This difference is E delta V, where V is the potential. Then I get J y equals E by L y times 1 over E b dV by dx times the density, which is E b over H cross times Ly over 2 pi. So, this is equal to, this Ly cancels, Eb cancels. This integration over the sample gives me delta mu or delta Ef, which is equal to E times the potential difference delta V. So, I end up getting E square 2 pi H cross is H times delta V, and that is J y or I y. So, this was I, the total current. So, delta V over I is equal to H over E square. And as I showed you earlier, current is basically flowing through the edges. If more than one Landau levels are filled, then the current is going to be equal to E square over H times the number of Landau levels filled, delta V, and you get delta V over I equals H over E square 1 over nu. What we mean by this is that in this sample now, you had earlier the ground state Landau level, now you can have the next level also. So, if there are two, you will get two of these Landau levels participating, and you get 1 over 2 H over E square. So, these are known as edge modes, because essentially dV dx is not equal to 0 near the edges, and the current is flowing only along the edges. In technical terms, this is what is known as chirality of the system. Right? There is this current flowing only along the right or the left hand side. Now, classically, you can also interpret it. If you were to interpret it classically, just to make a picture in your mind, if you look at this sample from the top, here is B field coming out. The electrons would be making a motion, circular motion like this. Let us see, this is V. So, V cross B would be to the left, and V cross E minus E V cross B will be like this. So, the direction will be opposite. They will be making these motions. So, within the sample, inside, the electrons are doing this. But what happens on the side? They cannot complete the circle. So, they move or drift in this direction. On the right side, they move like this. So, you can see that transportation is actually taking place along the edges, and that we explain quantum mechanically also by looking at the Landau states when electrons move even quantum mechanically in crossed E and B field. So, that is the classical interpretation. And since we did delta V was calculated using dV dx dx, which finally gave me delta mu, this is epsilon Fermi right minus epsilon Fermi left, it does not matter what the shape of the potential inside is. If it is flat and on the sides it goes up, then certainly all the current is taking place along the sides. And finally, I want to give you a beautiful argument by Laughlin. This is a 2-page paper and is among the 50 most influential papers, but it explains this through the gauge invariance of the system. Now, what Laughlin argues is that since quantum Hall effect is robust, that means you put disorder in the system, you increase the disorder, right, you still see it, it persists, and that the integer nature of nu and the quantities E square by h and all that, they do not depend on the disorder. This implies it must be based on fundamental principles and not depend on the details of the system. And the fundamental system principle that he invokes is the gauge invariance of the system. So, what he does is makes a Hall system which is like a annulus strip. So, this is the filled strip. So, this is the annulus strip carrying current I. So, here is current I flowing in it. And it is put in a magnetic field over the strip. So, this is like a quantum Hall system, right. So, let me make this strip again. Here is current I and here is the magnetic field B only over the strip, and what is going to happen is that there is going to be Hall effect. So, inside will get positively charged and outside will get negatively charged, and there is this V Hall in between. Now, what you do is introduce a flux in the empty region at the center. So, what you are doing is taking this annular strip and introducing a flux right here. as you introduce this flux, is going to generate an electric field. And there is already a magnetic field here. So, let us make this electric field right here. This is a magnetic field, and this is going to make electrons drift out. That is what we learned. If you have crossed electric and magnetic field, electrons can drift out. So, in this Hall system, electrons are drifting out. Now, if you did the flux quantization exercise I gave you in the last lecture, you learned that if phi is equal to phi naught equals h over E, E over h, then this just introduces a phase in the wave function. Such that phase is e raised to I 2 n pi, and nothing changes in the system. So, as long as electrons are mobile, they are going to move out, and when phi equals phi naught, this is going to, the system is going to come back to its original thing, but something has happened during that time. So, here is this annular shape, and there is B, and you introduce this phi. Consequently, electrons get transferred to outside, and when you go to phi equals phi naught, system is identical to the original system. And remember, I had this current I going around, but certainly when I changed the flux, we did some work. Phi naught I, and where does this work go? This goes into transporting n electrons from inner ring to the outer ring. Of the annulus. So, you got to have phi naught I is equal to V Hall times N E, where N is an integer. Let me write this as nu. So, let us write this as V H nu E. So, V H over I, and V H is in y direction, I is in x direction, is equal to phi naught over nu E, which is h over nu E square. So, just from the invariance of the system under a gauge transformation, and when a flux of quanta 1 is applied and the system remains invariant, you got that the Hall voltage should be 1 over nu h over E square. So, this is independent of whether the system has impurities, whether the system has disordered states and so on. As long as there are these mobile electrons that can move from one to the other side, this is what is going to happen. So, this is Laughlin's argument. So, now I have explained the integer quantum Hall effect in 2 or 3 different ways. First, we looked at the Landau levels and their degeneracy and got an answer, but then we got a little more sophisticated and wanted to explain why the plateaus are there. That we explained through disordered states in the system, and then we looked at the edge states and how the current is taken in these systems through edges of the sample, and finally, we gave Laughlin's argument. All this has opened up many things. For example, when current flows along the system, this has given rise to a new topic called the topological insulators, whereby the system is conducting along the edges, but inside it is an insulating state. So, let me now conclude this lecture by stating precisely what I said just now. 1, explain quantum Hall effect, the integer one, by considering degeneracy of Landau levels and disorder in the system. 2, learned that current, which is the Hall current, in a sample flows along the edges, and third, gave Laughlin's argument based on gauge invariance. Thank you.